Hello and welcome to More Interesting Maths. I'm David Myers with UTC South Durham. True to the name of the channel, this is More Interesting Mathematics. I'm going to show you a few elements of mathematics that inspired me to go and study maths at university and also afterwards just for curiosity. This is maths for maths' sake, for you at home, your curiosity and your entertainment. Generic introduction clip over, now let's do some maths. For today, I'm going to be taking you through one of my personal favourite puzzles from another personal favourite website, Nrich. Most maths teachers will or certainly should know about the website Nrich. It's full of wonderful little puzzles and problems that anyone can have a look at home. This puzzle, Y8, I always use as an introductory lesson and exercise for any new class, just to show them that they can play with the mathematics at home. It's perfectly fine to just play about with an idea for a little while and see what happens. Looking at the problem today, it says choose any 4 consecutive even numbers, consecutive meaning next to each other, for example 6, 8, 10 and 12, multiply the middle 2 numbers together, aka 8 times 10, multiply the first and last numbers, subtract the second answer from the first. In this case we get 8. Let's see what happens. Now you might be trying this puzzle at home for yourself. You can have a scrap of paper. All you really need for this is said paper, pen, maybe a calculator if you want to make things a little bit more interesting for yourself. To begin with, what I want to do is just try it out. The best way to get to grips with any mathematical puzzle is just to have a go with some random numbers and see what happens. They said choose consecutive even numbers. So let's start, say, for instance, with 6. The next even number would be 8, consecutive meaning next to. So as even numbers go, 6 is next to 8, 12 is next to 10, and so on. So after 8 we get 10, and after 10 we have 12. 8 times 10, multiplying the middle 2, as instructed by Nrich, gives us 80. And 6 times 12, well, that gives us 72. And if we subtract 72 from 80, we're left with 8. Okay? Doesn't seem anything interesting so far. So let's try a different set of numbers. Let's try something, let's go a bit bigger, shall we? Let's go with 16, 18, 20, and 22. Yep, just check that I've got those right. I can remember how to add 2. Easter holidays haven't taken too much away from us just yet. Multiplying 18 and 20, we are left with 360. If you are very good with mental calculations, then you will be able to figure out that 16 times 22 is 352. Subtract those, lo and behold, again, we get 8. Okay, now this is starting to tickle our curiosity. Is there a way we can break that? Does that always work? The question to ask here is, what would a mathematician ask? And right now, that's you. That's you, the mathematician. You can ask whatever question you want. You might want to try it, say, for instance, with odd numbers. Let's go with 3, 5, 7, and 9. What happens there? 5 times 7, that gives us 35. 9 times 3, that gives us 27. Subtract 27 from 35, and once again, this 8 keeps appearing. Hence, I suspect the name of the video, Y8. Now there are loads of ways that you could play with this. A few of the ideas, some of my previous pupils have come up with, well, what if I try decimal places? What if I start with negative numbers? What if I added 3 each time? So you can see over here, in each case, we've just gone up in 2s. Do we get a slightly different pattern if we go up in 3s? What I would really recommend if you're interested in this kind of puzzle is to pause the video now and see what happens. A few other ideas that usually crop up, which are certainly worth exploring as far as I'm concerned, are negative numbers, decimals, and, as mentioned, going up in sets of 3, 4, 5, is there a pattern, and so on. Say, for instance, somebody might suggest starting with 0.5. Perfectly reasonable start, and then we'll have 2.5, and 4.5, and 6.5. Well, we're going to do a bit of a cheat here, but then again, I'm aware of the solution, so I can cheat. Half of 6.5, that would be 3.25. So that's what we're going to get if we multiply these larger values. And if you've done it with your calculator, or if you've tried any other form of number, you'll know that multiplying 2.5 and 4.5 will give you 11.25. So bizarrely enough, it still seems to work even if we deal with decimal numbers. So now we're really convinced that this is working. We haven't done anything known as a mathematical proof yet, but we can get around to that a little bit later. What about if we try it with negative numbers? I'm going to be really cheap right now, and I'm going to start with -2, partly because it makes the middle calculation incredibly easy to do. So starting at -2, going up to 4, 0 times 2, well that's going to be 0, and -2 times 4, that is going to give us -8. And impressively enough, 0 take away -8, that gives us a +8. So again, try it with any other decimals or negatives, see if you can break it. That's usually fun, and I usually offer that as a bit of a carrot, offering a bar of chocolate to the first kid that can break it. But let's have a look at some of the ideas that revolve around that. Let's try, for instance, multiplying by going up in 3s instead. So here we're going to start adding 3s, and we're going to see what happens. So let's add 3. Let's start with 1. Keep it simple. I'm convinced that it works adding 2 for now, but we'll see a more rigorous argument later. Let's go up in 3s. So 1 plus 3 is 4, plus 3 is 7, and plus 3 is 10. Well, 7 times 4, that gives us 28. And 1 times 10, that gives us 10. Oh no, that's a bit different, because 10 taken away from 28, that there gives us 18. We don't have to be convinced that it always works. Let's try a real base case. 0, 3, 6, and 9. Why do I know that starting at 0 works? Because 0 times 9, that'll give us 0. So we're going to be taking that away from 18. But that 18 has still cropped up. So when we add 2 each time, we get a common difference of 8. When we add 3 each time, we get a common difference of 18. You might want to make a table or something like that. See if you can try a few other numbers. Give it a go for yourself. So what you can see here, just a few more examples. All I've been doing so far, you'll notice, is playing with the mathematics. I've just been having a go with a few different numbers and seeing what happens. So over here, the +3, that hasn't gone anywhere at all. Well, what about the +5? Well, if we add 5 each time, then what seems to pop out is this number 50. Well, when we add 4 each time, we get a common difference of 32. Check it for yourself. Check as many as you like. All we're still doing is playing. One of the things that we can do to try and help us make sense of this is start making notes as and when we are ready. So say, for instance, if we were to make some basic table, let's go with a line, let's try and keep it neat. Let's say on the left-hand side, I'm going to write the common difference that we opt for, and on the left-hand side, we'll write the result. So let's do it in blue. Let's be fanciful. Oh no, that changed the line. Oh, never mind. So we'll call the common difference diff, and why not call it the result? What is it that keeps popping out at the end? We know that when we add 2 each time, we get a common difference of 8. When we added 3, we had a common difference of 18. 4, we got 32. 5, we got 50. So the question that a lot of mathematicians tend to ask is there a result? Is there a formula for this? Where does this come from? We don't know. First thing is, can we see a pattern in any of these? Well, the first thing you might have spotted is that they're all even numbers. And usually we like even numbers because they're a very subtle way of hiding some really pretty mathematics. So what we're going to try and do is see if we can find some general solution. The general solution is what will always happen. Can we predict what's going to occur if we change the common difference? So let's argue this out. If we know that there's a common difference of 2, let's try dividing all of these numbers by 2. We know that 8 is equal to 2 times 4. 18 is equal to 2 times 9. 32 is equal to 2 times 16. And 50 is equal to 2 times 25. Now, some of the more eagle-eyed amongst you might have spotted there's a pattern here already, looking at the numbers 4, 9, 16, and 25. And you would be absolutely right, because what we have here are commonly known as the square numbers. I'm assuming quite a few of you are familiar with these, but these are what we get if we multiply one number by themselves. Say, for instance, 4 is equal to 2 times 2, 9 is equal to 3 times 3, 16 is equal to 4 times 4, and so on. Why is that really, really exciting? Certainly for the mathematician, because that is what we started our common difference with. Over here, 9 is 3 times 3, and that is what we got there. That's brilliant, because that means what we've now found is a general solution. 2 multiplied by the difference squared, aka we should always get a difference of 2 times n squared. If you don't believe me, I'm going to prove that to you. What we'll do is we'll pick something wild and out there. We'll say I'm going to add 7 both times. But to begin with, I'm going to predict what the solution is going to be. And this is great because this is stuff you can try with less mathematically minded friends or people that haven't seen this kind of puzzle. You can show this off to them and get the right answer straight away. Trust me, I do it with the kids. They think I'm a maniac and a nerd. They are right in both cases. But let's do some mathematics very quickly in our heads. We are predicting a common answer of 2 times 7 squared. We can see this is going to get pretty big already because 7, I wish I hadn't picked 7 now, 7 squared is 49 and 2 multiplied by 49 is in fact 98. That is the result that we are going to predict. Now if we were to pick some random number and add 7 to it, let's go with 3. You might notice why I've done that. 3 plus 7, that gives us 10. 10 plus 7, that gives us 17. And 17 plus 10, that gives us 24. 10 times 17, 170. 3 times 24, well 3 times 20 is 60. 3 times 4 is 12. Add those together and we will get 72. I think most of you can see where this is going because we know that 170 minus 70 is 100, so take away another 2 and as predicted we get 98. So there we are, a nice little proof, or a bit of evidence rather, that we know exactly what is going to happen from any prediction. Now for those of you that are happy to keep playing with this puzzle, I recommend pausing and carrying on as you will. What I'm going to do for the slightly more advanced students, or for you at home, if you just want to see where maths really comes into its own, is prove that that is always the case. Okay, so in terms of proof, I might have been exaggerating slightly when I said it's always the case. What I'm going to do is prove our general ideas for what's known as the base case, the original question. I'm going to leave it to anybody who's into higher GCSE or A-level mathematics to prove the general case, and you can do that for yourself just as a bit of amusement. First thing that you should be wary about in terms of proof is it's an algebraic concept. Mathematically speaking, it's not proving beyond all reasonable doubt. It's not saying, well, I know it works for these examples, it must work all of the time. It is proof beyond denial for any and all numbers. What do I mean when I say that? We are going to start by letting our first number be n. Now you've picked loads and loads of numbers. You might have started with 6, 17, 4, 5, minus 17.2, whatever. N represents every single number that we could think of. any one of them. But we know from the original question, when we were getting a common result of 8, we added 2. So in this case, we can call the next number n plus 2. After that, we're going to add another 2, so that will become n plus 2 plus 2, or n plus 4. And then finally, add another 2 to that, and we will get n plus 6. From that, we need to multiply these two values. So for anyone who can remember expanding brackets, most people I know don't tend to be a fan of the grid method. I personally think it's a fantastic method because you can see exactly which combinations you have or haven't got, and you can just fill in the grid. Most people seem to prefer the FOIL method. Personally, I think that can get a little bit messy, but to each their own. What we've got here is n squared plus 2n plus 4n plus 8. That becomes n squared plus 6n plus 8. So we can throw that in here. N squared plus 6n plus 8. We now need to multiply these external numbers. N times n, that will give us n squared. N times 6, that will give us 6n as required. And if we take the difference, you can see that these two will cancel each other out. N squared minus n squared will give us nothing. 6n take away 6n will give us nothing, leaving alone plus 8 as required. There you go. Proof that no matter what number you start off with, if you add 2, and add 2 again, multiply the middle 2, multiply the external 2 and find the difference, you will always get 8. I will leave it for you to determine a proof what happens if you multiply by 3, by 4, or the general method. What I will do is write one little hint here that if you add any number, you can call that any number, then add another form of that any number, and do it one more time, you will find a general solution from that. So, ladies and gents, just to summarise, this has been a very brief overview of one of my absolute favourite exercises to introduce to a class that I've just met, and I think an absolutely lovely one to try at home. We had a very, very brief glance at the puzzle to see whether it works in general, and unsurprisingly we found that it does. We always get 8 when we apply this algorithm as specified. We tried a few other ideas with it. We decided to see if it works with decimals and negative numbers, and indeed it does. We took it a little bit further to see what happens if we add 3, 4 or 5, and then we realised that there was a very general result. If we call the common difference n, we always end up getting 2 times n squared as the regular answer. And finally, we proved that for the basic case when we add 2 each time. As a general exercise, I leave it to you at home, if you're curious, to see what happens if you call the common difference a, thus being able to predict any single solution. And that is it for this video, ladies and gentlemen. Thank you so much for watching. If you think it helped you out with your maths revision at home, then please click subscribe to get notifications on future videos. Share it with a friend if you think it will help them as well. There is a PayPal account, but please don't feel obligated to do that. 10 or 12 pence if you think that it's worth it for you at home and you liked the video and the content that I've put out. Failing that, thank you so much to Dr. Frost Maths for the slides, for UTC South Durham for inspiring these videos, and most importantly to you at home for watching. I'm David Myers. Take care.